IAPT mainly conducts examination for the students community. One of the examination is NSAP, which leads to the participation of Olympiad at national and international levels. There is another exam for undergraduate student, NGPE. In addition to this, there are so many competitions which are organized by IAPT, NCIEP, which stands for National Competition in Innovative Experiments in Physics. Similarly, national competition in essay writing in physics. At the same time, there is another competition, national competition in computational physics. These competitions are held every year and it is open to all the students and research workers, also for teachers. It also organize many symposia and activity-based programs, particularly for students and the teachers of physics subjects. It has Anveshika, NANI, National Anveshika Network of India, and many, many more. It also regularly publishes the periodicals, IAPT Bulletin, which is freely available to all the life members. In addition to this, Physics Education is a periodical which is published online, and it is also available on the website. Most of the work of IAPT is a voluntary work and contributed by many teachers, many research workers, student friends, different bodies and institutions also take part in the conduction of so many activities of IAPT. It has annual convention every year and it is open to all IAPT members. This is a brief introduction and it has its own website. Website deals with all the correspondence to be made for the examination enrollment and so on. So many things are taking place online now. So all of you are requested to visit the website of IAPT. Thank you.
Thank you, Boris, sir. That was a nice introduction about IAPT activities. Now, what can be a better way to remember an academician than conducting lecture series in his memory? So, Professor Dharkar, he was a great experimentalist. So, all the lecture series are based on some experimental methods. So, Professor Oglapurkar, sir, he knows Professor Dharkar well. So, I call upon Oglapurkar, sir, to share with us his memories and some experiences with Professor Dharkar. Please, sir.
Good morning, everybody. I was very fortunate to be in contact with Professor Dharkar for more than 20 years. I was introduced to Dharkar when I was NACP evaluator in 1997. Then our association went on increasing. In 2002, I retired and then I started working full-time for IIPT examination in consultation with Professor Dharkar. Yes, Dharkar assigned me the post of NSEP coordinator, whereas he was chief coordinator of IIPT examinations. I had the fortune to work with Dharkar for several years. From 2002 to 2013, I worked with Dharkar. He always insisted everybody that although I am chief coordinator, all the work is being done by Oglapurkar. He requested Arvind Kumar to invite me for all the National Steering Committee meetings. Once again, he said, I am the chief coordinator, but all the work Oglapurkar is doing. So better you invite him for the National Steering Committee meeting. Then for last 3 years, that is after 2013 to 16, I was the chief coordinator. Dharkar decided that hereafter I will not be directly responsible. I will always advise Oglapurkar, but I will not be directly in the examination work. So he assigned the chief coordinator post to myself, and I worked till 2016 for 3 years. Whether I was chief coordinator or Dharkar was chief coordinator, it was quite enjoying to work with him. Continuously, I got advice, cooperation, guidance, and whatnot from Professor Dharkar. He was well versed with all aspects of examinations and Olympiad program. So his advice was always correct and appropriate, most appropriate. For examination work, we traveled so many times to Hyderabad, Bangalore, Delhi. We met many VIPs like KV Commissioner and Director of ICER and so on. He always said, Oglavka, you first talk, and if anything remains or if anything is over, I will correct it. So he always pushed me that you first talk, and then I will just summarize. So that's how he gave me several opportunities, and I was very much impressed by his personality. Apart from examination work, Dharkar was a great appreciator. He had terrific reading, complete reading of English literature, Marathi literature, Sanskrit literature. He was a very good appreciator. Whenever he found anything good in either me or any of our friends, at once he used to appreciate that. So very good appreciator. He had correct judgment of many persons. Many times he advised me that don't take this person seriously. He is not a proper person. Or sometimes he always said, yes, you consult him. He is the right person to do this. He used to know which person can be helpful for which job, which task. So in this way, I enjoyed his company. I had valuable advice from him several times. He was very sincere friend and just like elder brother. When I was chief coordinator, I had many difficulties. Many times, some things, at least 4 or 5 occasions, something went wrong, and I was in severe difficulty. But Dharkar was always strongly backing me. He provided, along with Vijay Singh, Professor Dharkar provided me strong support, and I could always get rid of odd situations, difficult situations that arise time to time in my examination work. So this is all that I can say at present about Professor Dharkar. I will always remember him, and his memories always remain with me. In fact, whenever I do any work for IIPT, I always remember that Dharkar would have said this, Dharkar would have done this. So as if he's always with me for any IIPT work. Okay, thank you very much. I remember Professor Dharkar always, and that's all. Thank you.
Thank you, sir, for sharing with us your fond memories of Professor Dharkar, sir. That really gave us an insight into his personality. That's very nice and kind of you. Thank you, sir, once again. Now I request Professor Mahesh Shetty from Wilson College to introduce today's speaker, Mr. Uday Kashelikar, to the audience. Mahesh, please. And one more thing, if there are any questions, please put your questions in the chat box. The speaker will take the questions after the talk. Mahesh, please.
Yes. Good morning, everyone. Good morning, everyone who is in the Google Meet. Good morning, people who are on YouTube live stream. This is Professor R.M. Dharkar Memorial Series conducted by Mumbai IIPT, that is Indian Association of Physics Teachers. Professor Dharkar was head of physics department in Wilson College. He was also, of course, very active right from founding member of Indian Association of Physics Teachers. Has worked as a chief coordinator for various examinations, as Professor Oglapurkar mentioned. Today we have our guest speaker who is direct student of Professor Dharkar. Mr. Uday Kashelikar completed his BSc Physics from Wilson College in the year 1992. After that, he joined Nuclear Power Corporation of India as a scientific assistant, and then he was trained at BARC for many years. I mean, he was trained. He was a professional specialization in radiation protection and has experience of more than 3 decades in this field. He gave his services at Kakrapar Atomic Power Station, located in Gujarat. He was officer in charge of TLD lab, which he will talk about what are these TLD labs, and which is something which is very much responsible for quantification of dose accounting of radiation workers at nuclear plants. It is something really very important when it comes to the effects of radiation on the human health. and presently he is scientific officer in the Directorate of Corporate Planning and Corporate Communications, Mumbai. Contributes in creating awareness among the people about nuclear energy and radiation aspects. I would also like to add one more thing, that with autonomy of Wilson College, he is also on our board of studies and has been contributing, in improving, enhancing our syllabus. So we welcome Mr. Uday Kashelikar. Please.
Thank you. Hello.
Yes, sir. You are
able to hear me?
Yes, sir.
Okay. Thank you very much for that introduction, and also giving me an opportunity to speak on this forum on two counts. One is the physics teachers, for whom I have tremendous respect as such, and moreover, that physics teacher, the teacher who has trained us in physics, not only in physics, but those who are in Wilson College are aware that he was the convener of cooperative education program. So in 1991, when I was in second year, that time he was the convener of CEP, and there also we had a tremendous interaction. And whenever Sri Oglapurkar was speaking about the words that he used to tell, I can literally, it literally sounds in my ears how he would have said those words. So thank you very much, sir. And now I think let us come to the topic today. I will start sharing the screen. Yeah. So today's topic is understanding ionizing radiation. But before I start, I would like to come to this topic through the Nuclear Power Corporation's job that we are doing. So let us start. Now, directly I have started with this per capita energy consumption in gigajoule. This is the graph which is showing the per capita consumption over the period of time, over the period from 1965 to 2021. You can see the Indian graph and the whole world, everything. So it is progressively increasing. Now here we are coming to per capita consumption of electricity of various countries. Now these are not all the countries that I have taken in. I have taken it as a sample. You can see that the countries like Canada, Sweden, UAE, Korea, and you can see the countries like Somalia, Ethiopia, Nepal, and such countries. And the world average is given as 3081 kilowatt hours. Now, I think everybody, once the name of the country is taken, everybody knows whether the country is advanced country or having good facilities and the lifestyle. See, it is always very easy to find out, depending on what is the consumption, per capita consumption of electricity in that country, to find out the lifestyle of the country in a broader sense. Now, along with the per capita consumption, now we need to come to one of the very important part, that is CO2 emissions. We know that more than quite a big chunk of this electricity is produced by the thermal reactors. And the thermal reactors, one atom of carbon will have two atoms of oxygen, and it will produce a lot of carbon dioxide. So this graph shows you, please look at this graph. The graph shows that in 1965, the United States was having around 31% contribution. And now in 2021, China is having 31% contribution to the CO2 emission. And the line which you see is in absolute terms, the world release in billion tons. So we can see that the contribution profile has changed. You can see India in 1965 was having about 1% contribution to the CO2 emissions. Now we are having about 8% contribution. You can also see in 2020 there is a slight dip, and it is due to COVID, as everybody will know it. Now, why all this about carbon dioxide and energy consumption and all these things we are speaking? Now, we know that thermal power plants and nuclear power plants both are generating electricity. Now, here I have put this picture where these two bundles, which are weighing around 27 kgs, are equivalent to 700 tons of indigenous coal. And you know the kind of infrastructure it will take to bring that to the power station. And if the power stations are near to these places, then the kind of loss it will suffer when it is transmitted, when the electricity is transmitted. So now here things should be very clear that as much fuel we are using, there will be more waste. Now about the waste of thermal power plants, especially these coal power plants. You are aware about carbon dioxide, fly ash, SO2s and NO2s, everything. So they are contributing quite a lot to the environmental pollution in terms of greenhouse gases. Now the world is worried about greenhouse gases, and we as a nation have committed that by 2070 we will be almost reaching net zero CO2. So, but what is going to be the roadmap of reaching that net zero? It is not going to be a single nuclear power or a single solar or wind energy or different renewable energies, but it is going to be a mix of all these energies, and reducing the share of CO2 via these thermal power stations. So what we need to achieve is strike a balance or a proper energy mix which gives you a continuous baseline load operation as well as the peak power operations. Now some other day when we speak only about this, we can talk about all these things. But here now most of the people are a little bit worried about nuclear power plants owing to the safety of the nuclear power plants. It's not their fault, because the nuclear energy has introduced itself to the world through Hiroshima and Nagasaki. So there is a inherent fear in everybody's mind about what havoc it can cause. And then it was further enhanced by RBMK reactors of Chernobyl, and one very sad incident which was owing to the natural calamity of tsunami in Fukushima. So people have those things in mind. So that is one of the reasons why people are worried about safety. But if you see overall the world, if the safety records are seen, the most safest, you can say, the safest industry is considered as the aviation industry, space industry, aviation industries. And after that, the nuclear industry is coming very close. Now, perhaps it is not known to the world that what are the kind of safety and what are the kind of precautions that are taken in the nuclear power plants. That may be one of the route. And the secrecy behind these nuclear weapons and nuclear technology and prestige issue regarding this has further increased that enigma, we can say. So I would like to say that safety in nuclear power plants is achieved by, you can say, the first thing is redundancy. Now suppose we see that if the car is going very fast, and if you think that the brakes, when you apply, it will not stop, we'll always feel that danger. So we are having multiple shutdown systems which are independent of each other, which are not dependent on power. We can say, and it is a fail-safe method of shutdown which is applicable. So it is energized. It is energized to keep it working and de-energized to make it shut down, we can say. So it is fail-safe also. There are diversities. Diversity means that whatever the signals regarding the parameters are coming to control room are coming through various channels, and uh, three channels out of three, two channels, if the signal is seen regarding safety or anything, it is activated, and most of the time it is activated automatically. Similarly, there's a difference in depth approach, which we will come to see in the next slide. And there is a physical separation. What does it? What do you mean by physical separation? The safety systems and safety systems, you can say, or electricity, which is suppose there is no electricity, then there are generators and batteries. Class 1, 2, 3, 4 power supplies are there, and they are separated physically also, so that the fire in one place will not affect the other. Otherwise, you will have the four different sources of energy, but all of them placed in the same place, and can lead to some issues if there is a fire or some earthquake or something. So, along with this, I would like to say that safety is a moving target. So, what was safe in 1960s is not considered safe in 90, and which is now outdated in 2022. So, it is a progressive and moving target, which we continuously strive to maintain a very high, benchmark in the safety. And on the top of that, there is a robust regulatory mechanism which keeps us working. Now, this is about defense in depth. Now, I think let me tell you that we can see this. This is a secondary containment. Inside, it is a primary containment. This is the green color is the primary containment. This is the calandria. This is the channel, and this is the fuel. Now, the concern about radioactivity is all focused here. Now, from here, you have multiple barriers. First, the fuel itself is the barrier. Then there is a cladding of zirconium, which is the next barrier. This PhD system is the third barrier. Calandria and primary containment is the next barrier. And then there is a secondary containment. Now, these are the barriers which this particular radioactivity needs to cross before it reaches out of this. And beyond that, there is 1.6 kilometer exclusion zone boundary in which there is no settlement or nobody allowed. So we can say that after 1.6 kilometer here, the world begins. The remaining portion begins, where the people can live and we can say habitat. Now, this is the estimated dose which we can see at the exclusion zone boundary. Now, on the right side, the world average natural background, which also we will discuss about the natural background radiation, which is 2,400 microsieverts, and AERB. This is Atomic Energy Regulatory Board, which regulates all the nuclear power plants and nuclear installations, or medical and all kind of activities. The limit is 1,000 microsievert. So we can say that average world average of the natural background is what we are getting, whether there is a nuclear power plant or not, whether we are using X-ray machines or not, or we are not. Even when we don't know about any activity, any radioactivity. And this is 1,000 microsievert, which is the limit, which is even that is not. You can see the graphs of Tarapur, Rawatbhata. Rawatbhata is in Rajasthan, Kalpakam, Narora, Kakrapar, Kaiga, Kudankulam, all these power projects where it is almost on the ground. Okay, so it is not even 10% of the limit. Okay. Now the next things we are worried about is nuclear waste. Now you can see this, see the waste which is kept on the table, and that is the amount of high active waste. That is the amount of high active waste that is generated for the power requirement of Indian family for 25 years. Okay, and we can discuss about it in whenever we are going to talk about this. Now, coming to today's topic. Today's topic is, in short, we can say these are the 5 things that we will be going through. The first is what is ionizing radiation, what are the interaction of radiation with matter, then radiation dose and effects, about natural radiation background and medical exposure, and uh, interaction of radiation with matter. We'll discuss some in detail. Now, this is the first slide which is showing that what are ionizing radiations. First of all, what are radiations? Radiation is energy or particles which are emitted out of atom or nucleus. We can say that way. And even the light which we see, visible light, is also a kind of radiation. Then how are we saying these are the ionizing radiations? As the name suggests, ionizing radiation creates ionization while it is traveling through the medium. It is well known that whenever ionization is caused, it will be called as the radiation which causes ionization will be called as ionizing radiation. But it is not a singular radiation. Charged particles like alpha, beta, and protons, these are directly ionizing. We can say that Coulombic forces of these alphas. What are alphas? Alphas are nothing but helium nucleus. So it is 2 proton, 2 neutron. So it is positively charged. Betas are nothing but electrons that are originating from nucleus. And protons, as the name says, they are the protons positively charged. So either they are positively charged or negatively charged. So they can cause direct ionization in the medium. And ionization is possible through uncharged particles like neutrons. And ionizing can be caused by electromagnetic radiations, which are X-rays, gammas. These are called as indirectly ionizing. Now we will see further. Now this is the spectrum which everybody must be aware that based on the wavelength, we can say the quantum of energy that it has. But hardly we calculate the energy. This slide shows what are the energy scales. We can say that gamma is going to million electron volts and radio waves nano electron volts. So we can say that more the energy, see all these gammas and X-rays and gamma rays are ionizing radiations. Now, so you need a certain amount of energy to cause ionization. That is obvious. Now, once we know that there is something called as ionizing radiation and it can have bad effects or it can have good applications, we need to have some quantification for that. So in the history, the first quantification was the amount of charge that is produced in 1 kg of air. So 1x was 1 coulomb per kg. As you all must be knowing that coulomb is quite a unit, quite a large unit. And then slowly it was, as you can see that Ranjan may be aware about because of he has received Nobel Prize also. So here you can say 2.58 into 10 power minus 4 coulomb per kg is the smaller unit which is kept. So this is how it was measured. But later on, all this ionization is happening and its effects or applications that we can use, we need to come to energy which is absorbed from that wave, whatever energy that is absorbed in material, whether it is a human body or it may not be human body, it may be anything. So joules per kg, this is the SI unit of absorbed dose. which is called as gray, and there is one more unit which is called as sievert. Now, joule is irrespective of what radiation is exchanging that energy. Suppose alpha is giving you some energy, you in the sense any body, or beta is giving the same amount of energy, and gamma is giving the same amount of energy, its gray will be same. But when it comes to biological effects or its effect on body, it will depend on how densely those ionizations are happening. For example, in case of alpha, within the matter of few millimeters or micrometers, the whole energy, the alphas are having energy of the order of million electron volts. That entire energy is going to be deposited in a very short path. So we can say that if those in that short path, the number of cells that will be coming in touch with the radiation will be more compared to the gamma, which will be having a range of meters. Okay, and the beta also, which will be having the range of centimeters. So there has to be some weightage which is assigned to the radiation weighting factor. So this WR which is mentioned here is called as radiation weighting factor. It is 1 for beta and gamma, and it is of the order of 20 for alpha. And for neutrons, based on the energy, it is different based on that energy. So it ranges from 2 to 15. There is a mathematical function, will not go deep into that. So I would like you to remember these two things. One gray is 100 rad and one sievert is 100 rem. Now rem is Röntgen equivalent men, we can say, and these units will be coming through. But whenever we are going to measure, it will be like microsieverts. It will, or millisieverts at the most. Okay. And gray is also quite a big unit. Now we'll come to acute radiation effects. What are the radiation effects? See, if you remember 25 to 100 rad, 100 rad is 1 gray. So 1 gray is 1 joule per kg. So if that much energy is absorbed, only after that you will have minor blood chemistry changes which are visible or which can be detected. Next comes 100 to 200 rad, where the white blood cells loss can be seen. Greater than 250 rads, acute radiation symptoms start. Now, such kind of symptoms are observable only when, in the cases like, say, RBMK, that Chernobyl reactor, or some accidents that have taken place, not about the nuclear power plant accidents, but the source was stolen, or the sources were misplaced in the medical facility, or some accidental exposures in irradiating facilities. So we'll never come across this, but these are the levels. The next is, we can say that LD 50/60. Let me define this term. LD is lethal dose, and 50/60 means 50% of the victims will die in 60 days. So, and there is one LD 50/30 also. So this is how it is defined. I'm just trying to show the scale so that when we have a look at what are the natural doses and the quantum of dose that we are going to witness when we are going to have some medical exposure are minuscule. We can say micro gray level. Okay. Now, when we come, first what we have seen, that those were called as the deterministic effects. Now, there are two types of effects. These are the deterministic effects. And the second kind of effect is probabilistic effects. What are the probabilistic effects? As all the people are aware, are worried, it is somatic effect and genetic effect. Now, what is the difference between probabilistic effect and the deterministic effect? Deterministic effects have a threshold. Below that threshold, the effect is not seen or observed, and we need not worry about that effect at all. Whereas the probabilistic effect is the good example of probabilistic effect in day-to-day life when we say that cigarette smoking can cause cancer. Now, there is no direct calculation that how many cigarette one has to smoke to get cancer, because if you see, you will be finding somebody who is having lung cancer who does not smoke at all, or maybe smokes one cigarette a day, and you can find one 80-year-old healthy person who smokes more than 20 cigarettes and some 10s or some 20 bds all his life, and but he is still safe. So this is the probability. So we can say that the probabilistic effects are do not have any thresholds, but only the probability increases. Now, for probability, as you know, that we need to have a big sample space, and the effects are studied, and those effects are studied. Now, in this case, we can see here on the screen that around victims of Hiroshima Nagasaki, which were followed up for 47 years for the lifespan studies, and also the children born within 2 kilometers of the hypocenter at the time of bombing, and which were compared with the control of 41,000, and statistically there was no abnormality found. And this is not we are claiming, this is what has been studied, and it is widely published by International Commission for Radiation Protection and Indian Atomic Energy Agencies. And the probability of cancer is given as 5.5% per sievert, and heritable effects are 0.2% per sievert. Now how these things are studied? This five, what do you mean by 5.5% per sievert? Suppose there are 10,000 people who are exposed to one sievert dose, and the 10,000 people who are not exposed. The incremental probability of cancer will be 5.5 out of that. So 5.5% of that. That means that those who are not exposed, suppose out of those 10,000, there are 50 people who have got this effect, and here those who have got one sievert dose through his lifetime, they'll have 5.5% more chance of getting. Now here we are speaking about sievert. The dose limits and the doses that we receive are in millisieverts, and that too not even 1 millisievert is the average of the radiation workers. So we can say, and further, if you are worried about the nuclear power plants, which may be emitting some radioactivity and reaching you, so beyond that 1.6 kilometer, it is not detectable at all. In fact, inside also it is not detectable, but outside there are separate agencies which are doing this follow-up and trying to find out. So this is the kind of radiation that we are dealing with when we are dealing with power plants or applications. Now let us have a look at the natural background radiation. Now, most of the people nowadays have a thinking that whatever is natural is safe, and whatever is unnatural or created by human beings will have an effect which is going to cause something. So now let us see what is the natural background radiation. Now, where from this natural background radiation? See, we can see here that cosmic radiations. Now, cosmic radiations are coming, and we are highly protected by for the cosmic radiation because of the atmosphere. But still, there is some amount of radiation that we receive. It is not the direct radiation that we are receiving. It is the cosmogenic radionuclides also that we are getting exposed to. Now, there are two kinds of exposures. One is the exposure. One exposure is when the source is outside the body. So, X-ray machine, the source is outside the body. It is switched on. Some rays are passed through your body. The exposure is done. It is over. Second thing, it is internal exposure. When the source goes inside your body. Now, where is the source? Now, all these radionuclide, see here, carbon 14 or tritium, or for that matter, potassium 40, uranium series, thorium series, which are all there in our soil. And how much they are there will come in next slide. In agricultural products. Now, somebody would have heard about high uranium content in some village in Punjab. It was found that it was all because of the fertilizers. Those fertilizers were having high phosphate fertilizers tends to have a good amount of uranium in traces. So this is how you don't need to have a power plant to get exposed to uranium. Uranium is all over. Now see the soil. This is the ordinary soil which will have around 0.3 to 12 grams per ton of uranium. And then you will say that what do you call as ore? Ore is 0.2 to 2 kg per ton. But even this small amount of uranium is good enough to cause a lot of dose to us. Because uranium itself does not cause the dose. As you must be knowing that there are 4 natural series, 4n, n plus 1, n plus 2, n plus 3. So those series will have daughter products, which will having mainly radon and thoron daughter products, which will emanate out of the soil, and whatever we are using to build house or wherever you are going, they are with you. So we say that the radiation is the constant companion of the mankind. So right from the world and the human beings are created, it is there with us. Then seawater. Seawater is also considered as one of the important source. We have 3.3 micrograms per liter uranium in that. Now, where from this is coming to sea? One is the seabed, and second is that the rivers are flowing and reaching. So the earth is full of uranium, and that earth is contributing to the water, contributing to the salt as well as this uranium. And here it is very surprising that the uranium is even more plentiful than antimony, beryllium, gold, cadmium, and all these elements. Now there is one striking study about coal fly ash. Now coal is also coming from mines, and coal also contains quite a lot of uranium and thorium. So there is huge radioactive contamination even from fly ash. So this is the reference also is given. The quantities will come in next. Now here it is a pictorial representation of how we are exposed to natural radiation. Now we have seen that cosmic radiations are creating cosmogenic radionuclides which are coming down with rains and fallout. And then here we can see that from soil, this radon daughter products, it is coming. And in the house, when it is coming through your shower also, that groundwater. So radiation is all over and we are surrounded. There is nothing called as thoron. It is radon 220 is called as thoron because it is mainly coming from thorium 232 series. Now we say that not only we are surrounded, but we are invaded also. We are invaded by radiation. You eat rice, leafy vegetables or anything, it will have lot of radioactivity. Now we spoke about uranium, but also there is one very important radionuclide which is called as potassium 40. This potassium 40 contents are given here, becquerels per kg. Now I think everybody will maybe knowing about becquerel. Becquerel means 1 disintegrations per second. So if any sample contains a source which is giving you one disintegration per second, that means there is one transformations per second happening, it will be termed as 1 becquerel. So along with that, if it is an alpha emitter, there is 1 alpha coming out per second, means that the source is having the activity of 1 becquerel. Now all are knowing about Madam Curie. Now Curie is also one of the Curie is a very huge unit. Now what is the relation? 3.7 into 10 power 10 becquerel is 1 Curie. So when you say 1 Curie, it is a huge amount of radioactivity that we are speaking about. And when we say becquerel, becquerel is also not very small. It is 1 transformations per second or 1 disintegrations per second, leading to, say, if it is alpha emitter, then alpha. If it is beta emitter, then most of the times beta and gamma both are associated. Alpha and gamma also are associated. So both alpha and gamma will come per second. So 1 disintegrations per second or 1 radiation spike per second you will register. Now, just I told you about the fly ash content. You can see the bituminous fly ash, coal fly ash contained 30 to 217 becquerel per kg, and thorium of 10 to 120 becquerel per kg. Potassium and uranium contents you can see. So we can say that even the thermal power plants are also doing the radioactive pollution. Now you are aware about this medical. Now what I am trying to discuss is the kind of radiation that we are getting exposed to in our daily life. The first was natural radiation, and these are the man-made radiation which are for the benefit of the humans that we have devised. Now you can see dental x-rays, microsieverts, then chest x-rays, 100 microsieverts, spinal x-rays, this abdominal x-ray. So, and if you go for CT scan, you can see full body CT scan. These are the high numbers that we come across, but still we don't mind doing it. And definitely you are getting dose, but in radiation practice there is one there are actually 3 things. First is justification. So for any practice, to give any dose, there has to be a justification. What do you mean by justification? So it does more good than the harm. So this is the justification. Now in case of cancer treatment, one takes a lot of dose, but that dose is evaluated, and it is known that it does more good than the harm, because if by not using that dose, what are the impact on the life of human, and what are the impacts by taking that dose. So that is the first is optimization. Second thing is first is justification. Second is optimization. So the cost that we pay, not only in terms of money, but in terms of the detriment. Detriment is whatever negative impacts we will have, that should outweigh. First, we have seen that should outweigh the benefits. Second thing, even if it is outweighing, you should not go to an extent which is maximum permissible. You should try to go to lower level, as low as reasonably achievable. So that is how the radiation practices are carried out. Now all these problems are happening, all these radiations are interacting, and they're giving us dose. Sometimes they are useful for us. Sometimes we are afraid of it. So, but how this energy is being transported to us, we'll move there. Now here we can see the penetration power. The alpha, we can say it cannot even cross the paper. Beta, it is crossing the paper, but a thin aluminum foil cannot pass it. Gamma is crossing all these barriers, and it needs a quite thick shield of lead to prevent the penetration. And neutrons, you can say that they are going straight away. So, but even lead also it is going through, because it does not give any energy exchange. It gives best energy exchange in water or concrete or hydrogenous material. So, okay. So the first we have actually already discussed about alpha particles and beta particles, which are directly interacting by Coulombic force, and that is how they get ionized. They get the medium ionized, and then there is one more thing which is called as bremsstrahlung. Now, bremsstrahlung, when high velocity charged particles are suppose they are traveling through lead. Now, the high particles, when they are moving, they will be tremendously slowed down, and that slowing down process, when the charged particles are decelerating, they will create bremsstrahlungs or electromagnetic radiations. Now the fraction of bremsstrahlung is 3.5 into 10 power minus 4 Z into E. So as the Z is increasing, the probability, not only the probability, the more fraction of energy of beta will be converted into bremsstrahlung. So now earlier they were beta particles or charged particles. Now once they get converted into bremsstrahlung, they are electromagnetic waves. Now they will be able to pass through your that shield also at times. So while we are shielding for beta particles, we should not say that we will shield for beta gamma together. So let us put this lead, because lead can create an impact by creating bremsstrahlung. Now when we are doing counting, when we are doing radioactivity counting or activity counting, uh, there are chambers of there are shielding chambers in which the sample is placed along with the detector. The inner wall of those chambers are normally coated, or we should not say coated. In fact, there are thin aluminum sheets which form the inner part of the chamber, because the sample will contain some amount of beta. That beta will interact with lead and will give bremsstrahlung, and that bremsstrahlung will in turn disturb or will create a noise in your reading, and the activity calculations will be affected. So we need to use the shield intelligently. Now, neutron interactions. Neutron interaction, mainly elastic collision is important, and they are slowed down by elastic collision, and then they are captured. How they are captured? There are materials like boron or cadmium which will absorb the neutrons, and the probability of those neutrons getting absorbed depends on the energy of the neutrons. Now, most of these neutrons are going to get absorbed when they are thermalized. Now, what do you mean by thermalized? Thermalization is the kinetic energy of those neutrons is same as the kinetic energy of the molecules at that temperature in air. So the thermal neutron will have a different meaning when it is 50 degrees Celsius and 200 degrees Celsius. So that is what is thermal neutron, and that thermal neutron capture in lithium, boron, cadmium. These materials are called as poisons. These are also used in reactors for slowing down, not slowing down, but for shutting down the reactor. Slowing down is a different thing. And activation of radionuclides, activation of nuclides. Now we can say that these neutrons, when they are these neutrons, when they are meeting the different elements, like say cobalt 59, then cobalt 59 and neutron will become cobalt 60. Now this cobalt, why I'm taking the name of cobalt 60 is because cobalt 60 is used in the treatment of cancer. Then similarly, there are other radionuclides which are called as activation products. Those activation products often are seen in places where the neutron fluxes are high, either in accelerators or in nuclear plants. And hydrogenous material, see, what is neutron? Neutron is having mass of 1 unit, and hydrogen also has the mass of 1 unit. So their collision gives you a very good energy exchange, and it helps you in reducing the velocity of that neutron, which in turn will thermalize. The number of collisions it requires, it depends on number of collision it requires. If it is heavier material, it requires much more number of collisions, and for smaller ones like hydrogen or deuterium, it will have a better result in terms of slowing down. So once they are slowed down, they can be captured very easily. Now after neutron, the most important is gamma interaction. Compton scattering and pair production are very two important interactions that gamma undergoes. Compton scattering, as you must be aware, Compton is the interaction of photon with the electron, and it gives some amount of energy to that electron and leaves with the reduced energy, or we can say alternate wavelength. Here it is shown the energy which is the energy before the collision is P is equal to 0, and this is E is equal to M0 C square, which will reduce once this interaction has happened. The derivations are also we are doing in second or third year. Now pair production. This is a very interesting thing. What do you mean by pair production? It is just like producing electron and positron out of thin air. So it is from energy, there is a material happening directly. So that interconversion of mass and interconversion of material and energy, matter and energy is seen here. Whenever this incident photon is coming in the electromagnetic field, very strong electromagnetic field of nucleus, or even in the electron also, but it will create an electron-positron pair. So that is how the interaction will happen. Now, what will happen to these electrons? Now, these electrons, even in case of Compton scattering, and these electrons are now going to deposit all their energy in a very short range. And suppose if it is in your body, then it will deposit very shortly, and remaining part of photon will go out. The remaining energy of photon will go away. And at times even that will also get deposited. And most important gamma interaction is photoelectric absorption. Now photoelectric absorption, almost it is the complete transfer of energy to the electron. So the gamma comes, it gives its energy to photon, to electron, and that electron deposits the entire energy in the vicinity, in that small vicinity of the body or the matter in which it is situated. And there are other reactions which are not happening outside. These are normally seen in very intense radiation fields, which are called as photodisintegrations. where the gamma will disintegrate the nucleus of beryllium, you can say. So here the example is given as beryllium 9. When gamma interacts, it emits neutron. Similarly, there is one antimony beryllium source uh, of neutron. Now, what happens is antimony is having a good amount of gamma energy, which will be used to eject neutron. So, this is how you create neutron source. Now, these are all interactions together. We can see the Compton zone here. This is the red line, which is photoelectric. So we can see that lower energies, the photoelectric effect is predominant, and Compton effect we can see more or less in all the range. And pair production starts only after 1.02 MeV, because that is the rest mass energy of electron and positron together. So that is the energy which is minimum energy required to form the pair. And this is the graph. We can say it is coming from here and reaching this. So this is the total interaction coefficient, we can say, the probability. Now we come to radiation detectors. There are different types of detectors. One is gas-based detectors, or scintillation-based detectors, and scintillation detectors. Most of us might have done some kind of experiment in GM counters, or would have studied GM counters. Basically, it is nothing but a tube, a gas tube, which is having one anode and cathode, which is charged, which is connected to the source. And the principle is, whenever the ionizing radiation will interact, it will create some ion pairs, and it will introduce some conductivity. And that conductivity means what? There'll be charges, positive and negative charges. Those charges will get attracted to the respective electrodes, and there'll be some amount of current, and the voltage pulse that we get as an output will be utilized. That is the principle of gas-based detector. Scintillation detectors, there are two types, but we'll not be worried about what are the different types of scintillators. In principle, the radiation will interact with the scintillator material, and it will emit light. And that light will be a measure of what quantity, what energy, what intensity of radiation it has interacted with. And then there are semiconductor detectors. Semiconductor detectors, as always, will have a depletion layer, which will be very important part, and that is only the sensitive volume. Silicon and germanium are used. Now we'll move. Now this is the diagram of this gas field detector. We can see the central anode and outer wall is cathode, and here whatever pulse we will get across this, that will be the measure of radiation that we are going to get. Now electricity. Then this is a block diagram of GM counter. We can see the high voltage supply here. Then so many times preamplifier is not required. This is the capacitor, discriminator, and counter. Now we'll come to some examples after this. So this is the setup. Now this is a GM counter, we can say. This is the stand, and this particular is the place. This is a place where we need to keep our source or whatever we want to measure, and this is the absorber material. This is the place for keeping absorber material. Now why we are trying to do is, we will see in this. We can see here that this is the shielding outside. We are trying to prevent any natural radiation affecting our experiment. and various various absorber thickness will be used for finding out what is the range of beta. Now we'll go to this example. Here, calculate the minimum thickness of shield for plexiglass and aluminum to stop the beta particles from strontium 90. The densities are given as 1.18 and 2.27 grams per cc. The energy of strontium beta is 0.54. Actually, when we are saying this energy of strontium beta is 0.54, it is the endpoint energy. So probably some of you may be aware that beta is having a continuous spectrum, and 0.54 is the endpoint energy or the Emax that you come across in strontium 90. Average energy is roughly 1/3 of this. But when we see the range of the beta, we can only find out what is the endpoint energy. So the maximum energy will have the maximum range, and that maximum range, once you measure in for any medium, you will come to know the scale of energy it has. So similarly, yttrium beta is also having 2.27. Now strontium and yttrium are together. So this is how. Now you can see these equations A, B, C, and D. These are not the theoretical equations. These are the empirical equations. These are formed, and we can always use these equations to find out what is the range. Now the range is given in grams per centimeter square. Now this is one way of showing you thickness and trying to make it energy, trying to make it density independent. Now if I say it is in centimeters, then I need to define it for every metal or every material that you use. Now here we have directly given, here we arrive at range in grams per centimeter square. So E max, you can see for R is equal to, we have just substituted the value, and the answer comes out to 1.1 grams per centimeter square. Now once you know that this is 1.1 grams per centimeter square, you can actually find out for plexiglass what will be the thickness, or what for anything, for aluminium or for gold, silver, whatever you want to use. So this is how. And the second easier method which is normally adopted is this. Now here on x-axis you can see the range, and on y-axis you can see energy. Now this is the range energy relationship, and here directly if you know one thing, now suppose you know the range which is marked here in blue, you can directly find what is the energy. Or if you know the energy, you will know what is going to be the range. So once you know the range, now this is going to be used to adequately shield, or sometimes when you don't know what is a radionuclide, you can try to find out through, and if it is a beta emitter, pure beta emitter like strontium, then you will not be able to do gamma spectrometry. That also we can see later. But this is how we can utilize the property of range. So that was one experiment which we can use. Now next, here we can see this is another experimental setup. Here the range will be calculated like this. See all the things, including 1 centimeter of air. This is the thickness of aluminium. All these things will be taken together when we are going to, even including this counter window of 1.7 milligram per centimeter square of mica. Even that will be included, because we are going to measure this range to find out unknown beta particle isotope. sorry, it is. Now, third example, these are the count rates which are observed, which is a pure beta emitter. Now, the property, what are the properties of radionuclide? One is energy. Now, second is half-life. So, based on half-life, also we can try to find out what is the radionuclide that is present in the sample. Now here the table is given where the counts per minutes on first day to 20th day are given. If you plot a graph and you are aware that it is given that it is only a single radionuclide, if you plot a graph based on graph, you know that A is equal to A0 into e raised to minus lambda t. So 0.693 upon 0.049 will give you the half-life. Now that half-life comes out to 14 days. Now you are aware that half-life of 14 days is phosphorus 32. Now if you want to further ensure, then you can do the range experiment and find out the energy also. So that will endorse your findings of this experiment. Now we'll come to liquid scintillation detector. Now what for this liquid scintillation is used? Now there are radionuclides like tritium or carbon-14, which are very soft betas of the order of keVs. Tritium itself is 18.6 keV endpoint energy, and carbon-14 is 156 keV. So these are the radionuclides which you cannot easily count with a detector who is having some window or window thickness. So what we do here is we prepare a solution of liquid solution and put the source in that, dissolve the source in that sample, not the entire source, the sample of the source, and put it for counting in liquid scintillation. Now here this schematic diagram shows you what is the liquid scintillation spectrometry setup is. Now you can see this is PMT1, photomultiplier tube 1 and 2. What is photomultiplier tube? It converts light into the electrical signal. So there are two PMTs which are connected parallelly here, and both of them, and this is you can say that this is a top view. This is a bottle in which you have put a source along with the liquid scintillation solution. Now, liquid scintillation solution is a beta emitter, is a detector itself. Liquid scintillation solution is a detector, and the beta source that we have put in is now in close contact with the detector. Now, it does not have any barrier, so that it will get absorbed in that window of the counter, like it would have in GM counter. Now, those betas will interact with the liquid scintillation molecules. In liquid scintillation also there are primary solute, primary solvent, secondary solvent, primary solute and secondary solute. It is having its own function. Like from beta, it takes the energy, it creates the scintillation. Now that scintillation, all the scintillations are not visible to the PMT. Each PMT is having characteristics for given wavelengths. Now those wavelengths, the wavelength of the detector, the wavelength of this light needs to be altered before it gets to PMT, so that it is properly counted. Now here it will collect the whole light and it will convert into signal, and then it will go to summation. Now, why this summation? We can actually discuss it. Suppose the beta event happens here, and the intensity of light here will be seen differently by these two, by PMT1 and PMT2. If it is here, it will be viewed again differently. So what we need is together, whatever the signal together is seen, that is there. And there is one more function of these two PMTs which are used in coincidence. Here there is a coincidence logic that whatever intensity that we can see, the spur of or a flash of light, it should be seen in both these PMTs in the given time window of microseconds. So of that order, and that coincidence pulse will come here. Only if it is coincidence, it will be treated as the source. Otherwise, it will be treated as a noise. And then now what will happen? Now the intensity of light depends on the beta energy. The more energy beta has, it will produce more light, and more intensity will generate more voltage pulse, and that more voltage pulse will lead to higher will lead to address of the higher energy. So depending on the intensity, the count is registered in a channel which is higher energy channel. So if it is 18 kV, it will go to 18 kV channel. That means the which is calibrated for it. So the counts will increase based on what are the number of counts for a particular energy, X energy. So if it is energy of 1 kV, 2 kV, 18 kV, depending on what calibration we have done, it can be either 1 kV per channel or 0.5 kV per channel. Now, next we come to gamma spectrometry. This is the most widely used technique for identification of radionuclides, because it is in a way quite simple once you have the equipment. So this is a detector, preamplifier, and this is low voltage. Now gamma spectrometry also you can do by two methods, we can say at least. One is scintillation method, which is almost like liquid scintillation we have seen, and another is a hyperpure germane HPG detector. This is solid state detector, which is semiconductor detectors. Now the detector will have interaction medium, and that interaction will create some signal. Now that will be taken by preamplifier and then further processed by amplifier, and will go to multi-channel analyzer, and we will get the output against intensity, not intensity, energy and counts. So we will get what are the counts for a particular energy of gamma. Now here I have shown the predicted response of gamma. Now depending on this Compton and single escape, double escape, we can discuss it when we have time for it. This is scintillation detector principle. Ionizing radiation comes here, scintillation happens. This is a photocathode. It will give you electron, then electron multiplier give you signal, and that signal will be proportional to the radiation, ionizing radiation, energy of ionizing radiation. Now here we have seen the advancement. Previously in old days, only sodium iodide was available. Sodium iodide detector is having a resolution which is seen in blue. Seen in red, and HPG is shown in blue. Now here you can see very thin lines. What do you mean by thin line is you can get definite answer of what is the actual energy of that radiation. Now here the source is cobalt 60 source, which is put, and the same source is put for sodium iodide as well as HPG. The sodium iodide, as you can see, is giving you a broader peaks at 1173 and 1332, whereas it gives a very sharp peak in HPG, hyperpure germanium detectors. So depending on the kind of requirement you have, we can use. Here what happens is the sodium iodide will be having a lower resolution but high efficiency compared to HPG. So when the quantitative measurements and very low radiations, low sources are there. So sodium iodide sometimes will be better off, or you can increase the counting time also if you want a good resolution of what are the different radionuclides present in the sample. No, I will not be discussing this dead time of the detector. We will come to the various instruments. Like say this is a teledetector. With as the name suggests, this is the extendable probe to around 3 to 4 meters, and this particular portion will be having GM detectors, two GM detectors, one for short range and one for higher range. Now this is neutron REM counter. This is used for measurement of neutrons. Now this is the polypropylene moderator material which is used for slowing down. This is He3 proportional counter. Now inside there is He3 field which is getting activated. Once it is getting activated, it will release protons, and those protons will be counted, and based on that neutron. So it is indirect ionization. We discussed first that neutron is indirectly ionizing. So if it is ionizing, then we need to simulate something. So first we have put this polypropylene moderator, which we have for slowing down, and then there is activation material, the material which will have a nuclear reaction inside, and that reaction is giving you protons. Now those protons are charged particles which can be counted. So that is the proportional counter used here. Now these are the various portable dose rate meters. We'll come to TLD. This is the thermoluminescence dosimeter. Now, as the name suggests, thermo is heat and luminescence is light. And using thermo and luminescence, we are going to measure the dose of the individual. Now, every individual who is working in the radiation field or going in active area is supposed to carry this. You can see a photograph of one person also stuck on that. So it is individually issued to individual, and it is to be used throughout the month, and that dosimeter will accumulate the dose or integrate the dose which a person has received throughout the month. Now this is the closer picture. Now what this TLD contains? TLD contains 3 discs, D1, D2, D3. Now the material is calcium sulfate dysprosium, and it is embedded in Teflon. Now calcium sulfate dysprosium embedded in Teflon, three discs are placed on a aluminium plate, and it is placed in this casing. And now you can see one red color. This is a metallic filter, we can say. It will not allow beta particles to go inside. This is the photograph. You can see the transparent part is plastic. So here also very strong betas will be able to go, and gamma will also go. And this is almost open window. Only a paper is there below D3. Now these are the 3 filters which are used in TLD to find out when we count it. The count in D1, D2 and D3, we have an algorithm which will show what is the dose the person has received. Now this is the band diagram. So whenever the radiation is interacting with this crystal or calcium sulfate dysprosium, there is excitation, and that excitation will lead to excitation of electrons, and then electron holes will be generated. Some of them will get trapped in the trapping centers. Now for that enhancing the trapping centers, there is one dopant which is called as dysprosium. The dysprosium is placed so that it creates this more number of traps, and more the number of traps, you will get more the number of efficiency. Now, how we have to derive light from this? We for every thermoluminescent material, there is a particular temperature which is called as a glow peak temperature. So you constantly start heating it at a particular point, depending on the trap depth and the crystal structure. It will have a particular temperature at which the maximum intensity of light will be seen. Now that particular glow peak temperature is achieved, and the area under the curve of that glow peak will give you what is the dose. This is pre-irradiation, post-irradiation. Now this is the actual, this is the reader, and here we are putting the TLDs, and then you can see like this D3, D2, and D1. Now you can see this person who has received a little bit beta dose and gamma dose also. So you can see this. The area under this glow peak will be a measure of dose that he has received throughout the month. Now let us see this. This is the characteristic glow peak. In India, what we are using is calcium sulfate dysprosium, and it is having its peak at 220 degrees Celsius. And these are the properties which are seen. Now, fading sensitivity, and so these properties are very useful for taking calcium sulfate dysprosium as the legal dosimeter for us. Even outside, people are using. First, it was lithium fluoride which was used, but this is indigenously developed calcium sulfate dysprosium. Now further we'll go a little bit about calcium sulfate dysprosium characteristics. Now here, this is the curve. If we are not using filter and we are having a bare disk, now we can see the huge response at the lower energies. This is because of the photoelectric effect that we have seen. That at lower energies, we will see a lot of spike. You can say a lot of energy absorption, and that is why you will see the more light. But we don't want we want dosimeter to be dose dependent, not energy dependent exactly. So when we put the filter, it will come down to this. So we will get the same dose irrespective of what energy dose, what energy has delivered that dose. Now I think let us see this. What natural dose we are getting is around 2400 microsievert, and man-made dose we can say around 600. This is the average dose that we get. If somebody doesn't carry out any X-rays, he will not get, but some people will have more number of interactions. So this is the average dose. So around 3000 microsievert is the dose that we get out of our activities or even inactivities. Even if we sit at home, we will receive this dose, at least 2400 dose. So thank you very much. I think I have been a little fast, but if many people will be having many questions, and I hope that some of the questions they will see by themselves, and some of them will ask today. Probably I'll be able to answer those. Thank you very much.
Thank you, sir. Your talk was very informative and yet very simple. You made us aware about the per capita energy consumption and carbon dioxide emission from different countries. I'm sure we have benefited a lot from your presentation on the properties of different ionizing radiations, then measurement of radiation doses, how they're different from each other, and how the radiations affect the different tissues in different way. Then different radiation detectors, the dosimeters, interaction of radiation with matter. All these things are very interesting. Thank you, sir, for taking trouble on Sunday morning and being with us. Now I call upon Dr. Shamla Bodne to handle question answer session.
We had earlier requested people to type their questions here, but no question has been typed. There is one comment over here. For textbooks, radioactivity is one equation, dN by dt is equal to lambda raised to n. Now we know why physics is called empirical science. I think this is a comment by Mahesh sir, am I right?
Yes, ma'am.
Yeah. Okay, anyone has any question? Uh, if there are no questions, then Hema madam, we can proceed further.
Yeah, I request Sushmita Mehta from Patu College to give vote of thanks.
Thank you, Hema Madam, for introducing me for vote of thanks. I thank Bhole sir to talk about IAPT in details. I thank Oglapurkar sir for talking about the legend Dharkar sir, who has been the backbone of IPT. I thank Mahesh Sethi sir, who has introduced Uday sir to us. I thank Uday Kalchikar sir for telling us so many things about radiation. With the growing fear of radiation all around, this is the need of the hour. He not only talked about what is radiation, but how it is detected. So we are enriched with so many things. Participants who are here, the organizers, and also those who have joined us in YouTube. Thank you, one and all.